Hello students, in this video we'll try to derive expression for magnetic field due to current carrying solenoid at some point on its axis using Ampere's circuital law. We already had derived expression for magnetic field of solenoid earlier using Biot-Savart's law. Today we will use Ampere's circuital law to derive magnetic field expression and let us see how to do it. So consider a solenoid and here you will have to widen your horizons of imagination. So listen and watch the video carefully. Consider this as solenoid. Now when you consider solenoid like this, you will have to assume some direction of current. So for now I am assuming that the current is like this. Okay, so if I don't want to indicate these wires, then the other way of showing the current carrying wires is by circles, and what I will do is for each wire going inside, going for each current going inside, I will put cross here, and here I will put dot because current is coming out from the bottom part of the wire, so you can put dot. Okay, and so this indicates that current is going from bottom to top. Okay, so in one of the figures we will not be showing wire, instead we will show dot and cross. So understand that dot is indicating that current is coming out, and cross is showing that current is going in. So now let us have fresh consideration of a solenoid, and say there are n turns. I will consider that number of turns per unit length is small n, that is capital N by L. Okay, and now I assume that dots are here and crosses are at bottom part. So what does it mean? What this indicates? This indicates that the current is going like this. Current is going like this. Okay, and now there is a point P somewhere on the axis, and this is where we want to find out magnetic field. So what to do? Now we want to use Ampere's circuital law. Okay, with Biot-Savart's law we already have one equation, but now we want to use Ampere's circuital law. And what is the law? The law is that closed integration B dot dl is equal to product of mu 0 and sigma I. So the very first condition to use Ampere's circuital law is you have to have closed loop. Okay, so first we will have to imagine a closed loop. So let me consider closed loop like this. Okay, and then I will consider points to be P, Q, R, S. Let me take this reference. Okay, let us consider this figure only. So we are interested in finding out magnetic field at point A, and this PQRS is the Amperian loop. So first consideration is Amperian loop. First step for using Ampere's circuital law is to consider Amperian loop. So where is our Amperian loop? PQRS. Second, whenever you use Ampere's circuital law, you will have to determine dl. In which fashion, in which direction you will choose your line elements for integration. So as indicated here, look at these arrows. These arrows are indicating the direction for integration. So first we'll go from P to Q, then we'll go from Q to R, then we'll go from R to S, and then S to P. Now, if you consider a ring which is having current like this, say these dots are indicating that current is coming out, this cross is indicating that current is going in. So if this is the current direction, and if you look at the magnetic field direction here, how do you determine? So curl your fingers like this, curl your fingers in the direction of magnetic field, and then you realize that magnetic field is along positive x direction for this current carrying ring. So I can say that along PQ, along PQ, B is also in the same direction. When you are going from P to Q, direction of magnetic field and dl both are same. So for PQ, I can say that B dot dl is BDL cos 0 or simply BDL. But what if I am going from R, Q to R? So when you go from Q to R, B dot dl is like BDL cos 90, okay, and that is 0. Similarly, that is true for S to P also. And when you are going from R to S, there is no magnetic field because outside solenoid magnetic field is 0. So we are coming down to this type of situation. See, instead of closed integration B dot dl, we consider four integrations: P to Q, Q to R, R to S, S to P. What is the advantage? Advantage is we know that when we go from Q to R, B and DL are perpendicular. This integration will be 0, isn't it? Say Q to R, Q to R, you are going up. Magnetic field is here, so angle is 90. B dot dl will be 0. So this integration will be 0. When you go from S to R, B is 0. There is no magnetic field outside, and hence this integration will also be 0. Okay. When you go from S to P, what is happening from S to P? You are going down, magnetic field is along positive x direction, and hence angle between B and DL is 90, and hence this integration will also be 0. So you are left with only one integration, that is from P to Q. And what is happening from P to Q? As explained here, when you go from P to Q, angle between B and DL is 0. So you can write B dot DL as BDL. So three integrations are 0, R to S, Q to R, and P to S. And then this is what we are left with. Integration, closed integration B dot dl is nothing but integration P to Q B dot dl. Now, what is sigma Q? What is sigma Q? So, sigma Q is the number of current or number of wires enclosed by Amperian loop. So, I need to know how many currents are here, how many current carrying wires are here. So, this formula will help us. Suppose the length is L, then I can say that total length is comprising of n length, and L length will have how many turns. So the number of turns n prime is n by L into L, or else n into L. And then the current sigma I can be written as n prime I, or else n L I. Okay, this is the total current enclosed by Amperian loop, and that is what we will be using here. Say PQ is the length, so number of turns per unit length into length will give me number of turns inside the Amperian loop. Substitute. So what is sigma I? Sigma I is number of turns into current in each turn. So number per unit length into current. Instead of L, PQ is taken. Okay, and this is what we have here. This is sigma I. Okay, and ultimately we get, on simplification, we get B is equal to mu 0 n I. And earlier also we had same expression. This is magnetic field of solenoid of infinite length, which depends on two parameters. Which are the two? N, number of turns per unit length, and I. Okay, so that is the topic. I hope you could understand. Thank you.